So I've been asked to talk to you about effecting change in the engineering curriculum. And what I'm going to say to you are my thoughts. They're not necessarily Heriot-Watt policy, but they've been influenced by the time I've spent at Heriot-Watt, as well as my many years working in the construction industry. Change. Why, what, and how? The image of this book at the bottom, I think, is one of the best covers I've ever seen on a book. The little person there, the inquiring eyes, saying why and what, is actually the cover of a book that my mother was given when she was 11 years old. And I think that was pretty enlightened of her mother in those days to give her a book like that. I'm an engineer, and I add to those two questions, why, what, I add the word how, because as engineers, that is important. So why am I saying those three words? I'm saying those three words because unless we've found ourselves in the question why, we're going to get lost. Why are we doing change? The second thing is, what are we going to change? We don't know what we're going to change unless we really understand why. And the third one is how. And unless we've got the two whys and the whats really as good foundations, the morass of don't want to do anything will wear us down, and we won't succeed in what we want to achieve. So these things are important. So the second thing I want to do is to then say to you, civil engineering infrastructure, that is the field that I work in, and using a systems approach, first of all, let's try and set the boundaries for what I mean. Is it, as down in the bottom left-hand side, the relining of the Jubilee Line underground tube? While the trains are running every day, this was done at night and they won a prize for it. Is it as in the bottom right-hand corner? Is it sitting at a screen, sitting at a desk watching 4 screens, having a tablet and running digital twins? Or is it all the words that are up in this word cloud that I have at the top of the page? Those words are these ones, and this is the way I define what the boundaries are of what I'm looking at. And I'm going to read it out. The planning, design, construction, operation and recycling of roads, rail, aerospace, ports and shipping, utilities, buildings, transport systems, energy supply, water supply, sanitation, flood mitigation systems, and city and rural systems. It includes construction method, including robotics and off-site manufacture, and construction management, including resilience and safety. And all of this is driven by economics, zero carbon, sustainability, the circular economy, the UN Sustainable Development Goals, and the incredible opportunities of real-time big data. It's a big field. It's an exciting field. I think it's probably the most exciting career that anyone could have, is moving into this. And the reality is that when we are training graduates in civil engineering, they may well go into any part of this, and we should be preparing them for it. We can't teach them it all, but we need to be preparing them for it. And as Rachel Skinner, the president of the ICE, has said, civil engineers have a central role in tackling climate change. So let's go to the why. Why change? There are 3 drivers. The one is climate change, which we're very much focusing on today. The second one, and in climate change, I'm including sustainability and the circular economy. The second one is the United Nations Sustainable Development Goals. And here we have a set of standards which we have said are right for civilized society. And this is an important thing for us to understand. This is what we're aiming at. And the third one is real-time big data. And I haven't just said big data. I very deliberately said real-time big data. And real-time big data is when a sensor can send a bit of information to a computer. Computer can do something with it, and it can send back almost instantaneously an instruction. And that process is a process which is really the great revolution which we're going through at the moment. So those are the three whys, and let me expand on the whys. Practically everything the construction industry and infrastructure does and civil engineers do result in harmful emissions and exacerbate the climate change. Practically everything that we do. And we need to be very clear that that is the case. This may come from embedded carbon in something we build or renovate, or it may be from the operation of the piece of infrastructure. And the interesting thing is that we're only doing it to make people's lives better. So there's a balance here. And it's important that our undergraduates are learning that they're moving into a situation of a balance, and they need to understand that balance and be able to cope with it. Paper in 2020 for the Association of Civil Engineers in the USA, Pierre and Logan, in their paper Reintroducing the Civil System Engineer, the Master Integrator, said, to appropriately face today's wicked challenges, the engineers must not simply solve problems, but help formulate them, both to define the problem and to find the best solution. And we need to partner with communities and involve people, ideas, and technology and technical expertise. It's great they said they're wicked challenges. They are. They're exciting challenges, but they are real challenges. And it's important to understand that they're saying that we need to partner with communities and industries, people, ideas, technology, and expertise. It is that together. So the next why, engineers have a reputation for inventing the wheel with every challenge they're given. Across the world, there are engineers simultaneously solving the same or very similar problems. The reality is there are big commonalities in the challenges that engineers are facing. I used to stand up and say, I don't know how many engineers in my firm were designing a 7.5 meter span reinforced concrete beam. And I don't know today, and I don't know how many designed one yesterday, and how many designed them last week and last month and last year. And what about all the other engineers all over the world? Surely we have designed every single possible 7.5 meter span concrete beam. Now, I'm only putting that as an apocryphal statement, but you get the message that I'm trying to get across. Data thinking brings the possibility to exploit this commonality, and our graduates need to be able to be thinking parametrics, flowcharts, and algorithms in order to deal with this challenge. Then there's big systems thinking. Our civil engineering infrastructure graduates will have to be comfortable with handling and controlling vast data sets. And they need to be comfortable with machine learning and AI. And I mean comfortable. I don't mean, oh, it's over there and maybe I have to be involved. They need to be able to embrace it and work with it. So my next question 5. This is a report that came out only in December last year. The current approach to delivering complex infrastructure is facing obsolescence. The sector is struggling to deal with the procurement, and complex systems need to be planned and delivered and integrated to provide mobility, energy, sanitation, infrastructure service on which people depend. The current systems are becoming obsolete. We need to be preparing our graduates for that change into new systems. So let's look then onto the what. And the what that I see, the whats that I see that are really critical, the silos. We are all working in silos. We can focus on one part of infrastructure, another part of infrastructure, another part of infrastructure. We're not bringing it together. The second part, as I've mentioned, are systems and processes. We need to be thinking in terms of systems and processes. And the third what is parametrics and algorithms. What? 1, data-centric engineering. To improve, you need to measure. And if you're going to measure, this means sensors and billions of them. And I mean billions of them. Currently, when we design a building, the architect will tell us what is good. The building services engineer will tell us what is good. The reality is they don't have the facts to be able to say what they're saying. They haven't actually measured the building. There are very few buildings we have which have measurements, have instruments in them and sensors in them, which are measuring what is really going on. And if we do start measuring in this way, and it is what we will have to do because we need to improve and we need to have those facts and we need to be able to manage those facts. And when you start putting sensors in places, it leads to civil liberties and learning what is being reasonable and proportionate and working with the likes of the organization Liberty. I worked at one time on security systems in major railway stations. And in that, we were using cameras. We were using cameras to find people who were behaving in the way that you wouldn't expect them to behave. And from that, we were able to detect those who were going to cause problems. But in order to do that, we have to discuss with Liberty what we're going to use that information for, how much information we're collecting on people. And we need to be able to explain that why we're doing what we're doing, why it is important, and why we should do it. Because if we don't, it won't happen and we won't be able to do our jobs properly. And all of this means that we have to have a practical skill that detects irregularities. When we run things through computers, sometimes we say, that doesn't seem to be right. And in the old days, we used to do a hand calculation to demonstrate, well, that's not right. Somehow or other, we have to build in the ability and skill to be able to detect irregularities. And then with that, we need to have the skills to work with programmers and to go into the algorithms and the computer program scripts to make changes and correct faults. What, number two, thinking holistic, doing stuff together with diverse others and moving from the siloed to the integrated. And I'm thinking big here. Take the water industry working with the electricity supply industry. Seems crazy. Why mix water and electricity? Well, the electricity supply industry is looking to ways to store electricity by batteries, by pump storage schemes, by all sorts of things like that. The challenge is that every time you store and every time you pull electricity out of storage, there is inefficiency. The fact is that the water industry is 24/7 pumping fresh water and foul water all over the place. And in some and many countries, it's desalinating 24/7. It isn't necessary to do those things 24/7. Desalination can be done when there is enough electricity. In reality, if we restructure our water industry so that there is storage with gravity feed, then we can be pumping when there is plenty of energy and not when there is a shortage. As the supply varies, coming from wind turbines and from solar and from other sources. And that means that we will be using our energy 100%. There is no loss when you switch off and only use it when it is necessary. That is what I'm talking about, thinking holistic, bringing it together. And it's the same with transport. Transport with communication. We've already seen in cities like London, when you use a system called City Mapper to find your way around, you make your bus system work. You could never understand where to go to. Now you can understand where to go to. We have bus systems all over the world, which are running on standard routes and standard timetables. This is history. We need to move to transport systems which are operating on demand. So they're actually going to and from where people want to go. And only then will we get people out of their cars. So the transport system has to work with communication. And this is what I'm talking about when I'm saying thinking holistic. Our students have to be able to think holistic. And then they have to be able to cope with robots on site, more off-site fabrication, more clickety-click assembly. It's quite interesting. We quite often get great off-site fabrication, and when it comes to putting it together on site, it's the old thing that we've been doing for many, many years. We haven't thought out how they actually all click together. It's digital twin control of construction and operations. And I've said construction and operations. I like to think of it as total virtual construction, that actually we virtually construct our buildings before they happen, and we're able to operate them on a computer. Ellen talked about waste in the construction industry. If we do digital twin in total virtual construction, we can eliminate a whole lot of that 25% of waste. And then the circular economy, total recycling and reuse built into things at the start. We need to be thinking this all the time. Whenever we are thinking about how we're going to use something in any bit of infrastructure and any building, we need to be thinking of it in those terms. So there we have it, systems and processes, parametrics, flowcharts, and algorithms. These are critical things that we need to change in the way we are getting our graduates to think and our engineers to be working in the future. We need to be familiar with using parametrics and flowcharts and algorithms in order to integrate things, in order to make sure that we're not doing again what was done before, and that we're building and all the time improving our systems. So how? Whenever one mentions change in the curriculum, the answer, the response which we get is the curriculum is already too full. And this is true. We all know from the time when we were students at university that the curriculum is very full and it's hard work. So how do we do it? Well, the first thing I want to say is work with the current curriculum. The fundamentals are necessary. I know that there are universities who are saying we don't need maths any longer, so we'll get rid of maths. I don't agree. Maths is vital, it's fundamental. It is the way that we become rigorous, and it's our rigor which is a really important part of what we're able to do. And it is the same with all the other subjects. The fundamentals are really critical and we must stick with them. The change we must make is to make that learning meaningful. So the students understand why. Why are they being introduced to this? How is it going to fit? What am I going to do with it in the future? Make that learning meaningful. So here's a diagram which was put together by Professor Paul Jowett at Heriot University and myself on how a civil engineering course structure could be seen as a system. In the center of it, you can see a line that says major projects. But by the way, this shows 5 years. Some courses are 4 years, some are 3. It doesn't matter. This can be adjusted to fit what the course, how the course runs. But in the center here, we have major projects in each year. Sometimes it's 1 major project, sometimes it's 2. Sometimes in 1 year there will be dissertations and so on and so forth. There is a core there of projects. And we need to use these projects as a steady development through the course to produce the capability and professionalism of our future engineers. So at the top, you can see the fundamental engineering knowledge, those fundamental subjects being introduced year by year, so that there is an outcome that our engineers have a toolkit, they have relevant knowledge and to be able to do their jobs. There is then the second level, and that is the applied engineering courses that we run, and the ability to apply and develop the knowledge that they got from the toolkit. And then the setting of it in the landscape, the global awareness, being aware of what different things do. Whenever we do something, we affect the external landscape. So that is feeding in there. And then using the projects to develop a systems thinking and process, step by step, gradually developing it. This is not adding to the curriculum, it's tweaking the curriculum so that we are putting it in a structure so that the students can see how they're going to go through their course, and they know what we're trying to achieve, so that every one of the academics knows how they are contributing to the system and why they're contributing to the system. And by doing that, we can develop our students to being systems thinkers, to be professional, and produce engineers that are fit for the challenges that they're going to face in that great big world, which I demonstrated to you earlier on. So use these projects to prepare students to appreciate the big picture. Use systems thinking, algorithms, and parametrics so that we are building on what is being done all the time. We're not going back to square one all the time, doing it over and over again, because there aren't enough of us to do it. We're always complaining there aren't enough engineers around. Part of the reason is engineers are doing again and again and again things which have been done before, and they should not be doing this. Focusing on the rigor that comes from an understanding of maths and being able to quantify and justify a solution. And developing individuals to be good at working in groups, being leaders, using stories, storytelling, and engineers who are savvy. Not engineers who sit behind a screen and do sums, come up with an answer, and expect the rest of the world to deal with it. If I can give you an example of this, perhaps a bit controversial, but in New Orleans, a way back when we had the major flooding problems, engineers had actually worked out what was going to happen. They'd written reports on what was going to happen, but they were told by their city fathers that there wasn't enough money to do anything about it. We have to learn as engineers not to stop at that point. When we know what needs to be done, we have to learn how to make it happen. And we need to be producing graduates who are prepared to do that for the future. So a couple of ideas on projects. I've talked about how projects are central to all of this. And I take one from the first year. We have a first year course where we bring together a whole lot of different student disciplines, 350 students together, and we work with them on climate change issues. We work with them on how to do presentations, how to set things up, how to get things done, so on and so forth. And in it, we have a period where we take the civil engineers and we set them up to be able to work in their particular discipline while recognizing what the big picture is around them. And this is the task that they're set. They've set this for 3 weeks. Their task is to work out how to provide water and good sanitation to a community, a new community of 30 houses. Nice and simple, quite small scale. They're working, each of the groups of students, there's 6 in each group, and they're representing varied countries around the world. So of course the challenge is different. If you are providing this for a community in a developing country, it's one type of challenge. If you're dealing with it in a highly sophisticated society, it's a different challenge. So they're working in different areas. And they have to come up with solutions that work for the country that they're representing, that recognize the local, national, and ISO standards and the requirements of the national regulator if there is one. They have to recognize the requirements of the United Nations Sustainable Development Goals. And they're told there is no electrical power for water treatment, nor for pipe, and there's no piped fresh water available in the area they're working. The proposal must be sustainable within the context of the country, so you have to think renewables. And the proposal should work in a way that effluent does not contaminate the local groundwater, and no effluent can leave the site except clean water. A contained system for 30 houses. It's a small scale project, but it introduces all of the issues of how we can actually provide what is necessary for 21st century living in a sustainable way. 3 weeks to do this project, and at the end, they present to each other. So they share with each other what it was like working in a highly developed country or in a less developed country, in a hot country, in a more temperate country, and so on and so forth. So they're learning to get a picture of all of this. And they're doing this, of course, before they've had all of the fundamentals being taught to them. So it's a really great exercise for them to go and research. Second project, which is a project which is given to third-year students in their transportation course. And it is a zero emissions parcel and small package logistics process. It's something called Magway. It's worth looking it up. It's a two-pipe system. It's not a hyperloop, which is massive. This is 1 meter diameter pipes, a pair of them, one going in one direction, one going in the other direction. They have little linear motor delivery units on track. And they deliver the crates, which are called tote crates, which are the size of the things which you receive your food in when the supermarket delivers it to your house. And it has been found that a very large part of the delivery of things around our cities and around our country can actually be contained in that size of packaging. So what we are asking our students to do is to design an installation for the Magway system. So the map here shows the central belt of Scotland. On the right-hand side, you have Edinburgh and Leith Docks. Well, docks is longer, but historic docks of Leith. On the left-hand side, you have Glasgow Airport and Glasgow, and you have the whole central belt development between it. And then you have Grangemouth, which is one of the major container ports of Scotland. So the groups are divided into two, so 9 students in each group, and they are asked either to design a route from Grangemouth to Glasgow or a route from Grangemouth to Leith. Okay, and they have to plan and design the routes. They have to propose the routes from a demand perspective. You have to evaluate demand to do that. They have to work out where distribution warehouses might be, where retail centres are, where the airports are, where there's residential communities, and allow for loading and unloading arrangements at each of these locations. They have to understand the existing infrastructure corridors and see what opportunities and challenges they bring. They work with Google Earth and other GIS information systems on terrain and land use and existing infrastructure. You have to pull all of these things together. Mass data systems, pull that information together and propose ways to evaluate the design parameters such as ground conditions, overhead restrictions, and so on and so forth. And incorporate arrangements at the container port to transfer the goods from containers or pallets onto tote crates and the automation of the distribution. And finally, they have to define how the last mile delivery is going to work, because you can't make this system go to every place. So it will be going to load and unload places. And there's a last mile process involved in it. It may be vans, it may be electric vans, it may be electric bikes, it may be walking. It's a whole host of last mile delivery arrangements. And then they have to evaluate the construction alternatives and their costs. Having decided whether it's cut and cover or it's bored underground, and so on and so forth. And then they have to put all of that together in a business case to Transport Scotland. And they have to go onto the Transport Scotland website to see what Transport Scotland calls for in the business case. So they're taking all of their skills and working together to try and put together a system which reduces contamination, and it also reduces congestion, which of course is part of the major challenge of our cities. So there we have it. Thank you for listening. I've tried to explain why, what, and how, as I see it, in the way of effecting change in the engineering curriculum. Thank you.